Okay, let's get started. So, are there any questions of any kind? So, what is next week? Midterm. Dun, dun, dun. Dramatic sound. Are there any questions?
Are there any practice midterms that we can go over?
So are you asking, are there any, or are you asking for us to go over it?
No, I was just asking if there's any.
Yep. Are there any questions? Okay, no questions then. So let's avoid the sample midterm and get right back into material unless there are other questions. Okay. So what have we been talking about so far? Vectors, well, generally what? Arrays, yeah. So we have arrays which can hold a bunch of stuff of any type that we want. So last time we were talking about several things. One of the main ones, the second main one, is multi-dimensional arrays. So we can have a grid of values like a 2D array, where we can specify the number of rows and the number of columns that we want. So in this case, we have 4 rows and 3 columns. So there are 12 elements in total. But I can specify 150 in here. So I can put any values I want. In addition, I could make any dimensional array. So instead of just 2 dimensions, I can make it 10 dimensions if I wanted to, and put a number for the number of quote-unquote rows for each one of the dimensions. So you can make this as general as you want to. There's not many uses for above 2 dimensions that I know of, maybe a few more than 2, but not really larger than 2, but you could if you wanted to. We saw ways to traverse an array, and we did a code example of that where you can either do it row by row, so I can look at the first row all the way across, and then the second row across, then the third row across, all the way down, or we can do columns in order. So the first column, then the second column, then the third column, all the way to the end. So that's what we talked about there. And the main thing that we started last time was this thing called vector, which will save us all. So what is vector? Yeah, well, it's a container that, what? It doesn't hold, well, it does hold arrays sometimes, but what is it generally doing? Yeah, it holds data. So it's mimicking an array, but it's an object. So we can call methods on a vector because it's an object. Can I call some function, some method on an array? So can I say like some array name dot some function name? No, so here's the difference. Can I call some function passing the array as an argument? Yes. So I can pass an array to a function. So the function just sits by itself and it receives arrays as its parameter. Could I take an array and say this specific array dot call some function on that specific array? No, and in fact there is no way to do that. Whereas for vectors, because they're objects, each time you call a function, it works on that specific vector. So if I want to add an element to a vector, it adds it to that specific vector. So let's see this in action. So let's just say I have a normal vector of int v here. And suppose I wanted to add 42 to this vector, randomly chosen integer. How would I do that? Yeah, so I would call pushback, but how would I actually write it? V dot pushback, yes. Pushback, and then the value I want, 42. So I'm operating on the specific vector that I have, this single object right here. I'm not calling a function and passing the vector into the function. Here I'm operating on the single vector, v. So if I do pushback on this one and I had some other vector some other place, the pushback is not going to do anything other than on that specific vector. So because we're calling it with the dot operator here, we're calling it on the specific vector. So if I call pushback, it's going to add 42 to the end of v here. Cool. So yeah. So let's review vector quickly. So it says it has a flexible number of elements and it can grow and shrink. Does it actually? What does a vector have as a data member? How does it store all of the elements that it has? An array. Can arrays grow and shrink? No. So this claim is not true. It is true, but it's misleading. So can an array grow and shrink? No. But can the vector make it look like it's growing and shrinking? Yeah. So what it can do, and I don't know what slide it was, but we talked about this, where we had a partial array and we had to maintain the number of elements that we put into this partial array. Vector does the exact same thing. So let's go back to our example that we had. So if we have this vector v, and let's just say that at the beginning, I'm going to initialize it with 10 elements. So this vector has an array on the back end with precisely 10 elements in it, okay? And I call pushback on v. So what's going to actually happen here? So let's actually just see what happens. So let's print the size of the vector. We haven't really covered this yet, but we will. So if you want to know the size of a vector, you print v.size. And then let's just see what actually will be printed. It prints 11. So the vector on the back end doesn't necessarily have to have exactly 10 elements as the size of the vector on the array on the back end. Does it have to have exactly 10? No, but we can make it look like it has 10. It could have 100 elements as the size of the array on the back end. But we're going to make it look like it only has 10. So let's see. So when we do 42 right here, then it's going to be inserted at index 10, or the 11th element in the vector. But let's see. Let's just say it really did have 10 elements as the size of the array. Let's say it really did have that size. And we call pushback 42 right here. How can we insert that into the 11th position where there are only 10 elements in the array on the back end? If there are only 10 elements in the array and I want to add it to the 11th position, isn't that illegal? So invisible to us, vector is doing a reallocation. So it had 10 elements before, but when we call pushback to try to put it an element past the end of the array, then what vector does, it reallocates a larger array, copies all of the elements from the original array over, and then puts 42 in the next position. So completely invisible to us, it's growing, quote unquote, but it's not actually growing. It's making it look like it is. So just be careful when you see claims like this where it says it has a flexible number of elements where, as you know, it has an array on the back end, and you know those don't grow and shrink. So that seems to be a little bit confusing. So just be a little careful when you see claims like this. Yeah, you don't have to specify the size when you define it, but it's a good idea to do so. Yeah, so space is automatically added as needed, and the way it adds it is whatever the size of the array on the back end was before, it allocates a larger one and copies all of the elements over. So it will always have enough room to hold the array as is. We'll talk about the STL at a later point. The reason why it's part of the STL is when we create a vector, we have to have these angle brackets with a type on the inside. So either like an int, double, string, or whatever. That is what is called a template. So that it means that you can put any type there that you want. But we'll get to templates later. So the way that you create a vector is you say vector, angle brackets, something on the inside. So int, double, whatever type that you want, you put that on the inside. If we want to have a two-dimensional vector, what should the type on the inside be? Let's say of integers. 2D vector of integers. So we'll have vector of something. What goes in the something? A vector of int. Yeah. So if we want a 2D vector, we would have a vector, angle brackets. The stuff on the inside will be vector of int. So you can make this 2D, 3D, whatever you want, just as easily as you could with arrays. If we want to access individual elements, or in the case of 2D, rows and then columns of the 2D vector, then you just use square brackets, just like you would with arrays. So there's no difference there. And it does the exact same thing. But the cool thing is that, I don't think it's on these slides, is that if you try to access an index outside the bounds of a vector, it won't actually let you. The program, I think, will actually crash, but let's see. So let's see what happens here. So let's say I want to print index, let's make this back to a normal vector. So this has 0 elements right now. And then we do pushback. How many elements are in the vector now? 1. Good. So if I want to print index of 1, what is this trying to access? Index 2. Oh, sorry, the second element in the vector. So, and that probably shouldn't work. And it does work. Let's try -1. Okay. So
Your whole life is a lie.
my whole life is a lie. You're absolutely right. Why is that not? Let's actually figure out why, because I actually don't know. I was very sure that that would not work.
Try and set up one of those loops again, dump all the contents of your memory and see what it does in that respect. Because it might just be protecting it, defaulting the output to 0 instead.
Yeah. So let's try that. So I equals 0. I less than or equal to v.size. So this will print past the size, and then see out v of I. Let's try that. Okay, so apparently there is no protection here. I thought there was. Apparently there isn't. So you learn something new every day. So don't do this. Yeah, don't be evil. Yeah, I thought that was I thought it did that. Never mind. So don't listen to me. Okay, so if you want to create vectors, there are several ways to do that. So here it says define a vector of integers starts with 0 elements. So you don't have to put a size here, an initial size. And so this will start with 0 elements. How can that be possible? Because there's actually no way, although given my track record, there probably is a way to define an array of 0 elements. So let's actually try that. So let's say we wanted to allocate a single normal array of 0 elements. This will probably work, and it does.
It's probably just a memory address with no data.
I should learn to stop talking. Not actually, but yeah, so you don't have to put a size here. So here it says there are 0 elements in the vector, whereas here you can say, I'm going to start with 30 elements. For vector, so this actually is a difference between vector and int in arrays. So what did we know about the default value for arrays?
That it's whatever is
That it could be anything. Whereas for vector, it definitely will have all zeros or the default value for whatever type you're working with. So for int, the default value is 0. So no matter what happens, the vector will have everything initialized as 0 inside the vector, no matter what. So if you wanted to have the vector start out with a certain size, but have every element initialized to some other value, maybe you want to start them off at 100, for example, then what you could say here is, I'm going to have 20 integers in here, and the default value will be 100 in that case. Whereas this one says, I'm going to have 20 elements and then initialize them all to 0. But whenever you have a vector, they're always initialized to all zeros, always. But something that's actually really cool is, one of the issues that we have with arrays is that we couldn't just say this array is assigned to this array, because as we know, the name of the array itself is just a memory address. So I can't just say one address equals another one. It won't actually let me do that. Here, we can actually do copying much easier. So I can copy the contents of one array into another much easier. So all you have to do is, if you want to create an array called scores that are the same values initially as the ones from this other vector called finals, then all you need to do is just create a vector event scores and pass finals in. So whatever finals had before, whatever its size was, whatever values it had, scores will have the exact same thing. So the same size, same contents, same everything. Another way you can do that is you can say scores equals finals, like this. So I can say I'm going to have my vector over here, and this actually does what you expect. It copies the values from finals over into scores. And so everything is nice that way. Another reason why you should use vector. What's another benefit that I can do because now I have an assignment taking place? And it has to do with this part. Do I need to specify vector of int here?
No.
What could I say instead? Auto, good. I can say auto right here. Why would this be better? Well, it's cleaner. It's shorter, and we all don't want to have to type as much. But there's a more important reason. What if I changed finals at some later point to be vector of double? Maybe scores can now have fractional parts. So if finals now, instead of a vector of int, is a vector of doubles now, and I just left scores as being a vector of int, would that be the same thing? No, it would do truncation silently. So by doing auto, it gets the exact type every single time. Even if you change finals, scores will change along with it. So use auto if you do this. However, you can't, for as far as I know, do it this way, because you're not actually doing an assignment here. So it doesn't know what the right-hand side of the expression is supposed to be because there isn't one. So if you're going to be initializing it like this, you have to put the type here. If you're doing an assignment, you don't have to, because you know the type of the thing on the right side. Okay, any questions about, yeah?
I have a question. With arrays, you could like initialize them to a bunch of different values, like you can individually put that. Can you do that with vectors?
Good question. I think you can. So what was it being asked was, let's see where it is. So this thing called an initialization list, where you have, instead of saying exam 00 equals some value and then initialize every single one on its own statement, just initialize the whole thing in a single line. I think you can. So let's actually try. But given my track record, it probably won't. So let's see. Yeah, so let's do this, and let's create a vector of ints this way, because this is a 2D vector here. And then let's set equals. Okay, of course it won't. Okay. I don't really know why that's the case. Non-aggregate type. Oh, okay, I see why. It's a complicated reason. Let's actually try it this way. Let's create a flat initialization list like this. And that doesn't work either. Let's try it this way. I think I might know why. I should learn to do these before I come to class. Apparently you can't. So, yeah, apparently you can't. And let's actually try to figure out why. Cannot initialize vector with initialization list. I doubt that's the reason, but of course it'll probably be the reason. Yes, it is. Of course, yeah. Of course it's the reason. So let's actually try to figure out why, because that's interesting. So what is actually being called when I do this? So when I create this vector right here, what thing inside the vector is being called when I create the vector? Or when I construct the vector? The constructor. Ah, good. So let's actually look at the constructors. So there's a lot of stuff here. So let's actually look at this. So you don't have to worry about like any of these up here. Allocator is something completely different. You won't have to worry about. So you don't have to know what explicit is either. But look at this one. So this this constructor takes something called a size type, which is like an integer. And this will tell how large you want the vector to be. So this is what we were doing before. What you can do in some other cases is you can pass in a vector here, and notice it's a const reference right here. So notice some of the principles we've been talking about, passing a large object by reference and by const. So you don't have to make a copy and you don't modify the original. You don't have to worry about these double ampersands yet, because we're going to get to that eventually. But look at this last one. So it says that you can take a vector of something called an initializer list, whatever that is. Look at the second argument. So what does the equal sign here mean, to refresh your memory? Well, an assignment, but in terms of a constructor, what does it mean for the argument itself? When you have something equal something, what is that for a constructor? Starts with D and ends with fault. It's a default argument. So do I have to pass a default argument? No, but could I if I wanted to? Yeah. So what happens here is we're calling this constructor right here. and it says we're taking a standard initializer list, angle brackets t, whatever that is. So what this thing is over here, this object is something called an initialization list, as we've seen. But there's an actual object for it as well. So if you wanted to actually work with initializer lists, this is the object for you. But the issue here is, as of a very recent version of C++, the meaning of the curly bracket thing on the right side can actually be an initialization list in some cases and not others. So in some cases, if we, let's see. Yeah, so in some cases, you can have an equal sign with curly braces and not compile, but if you remove the equal sign, it does compile. So this is one of the reasons why but you should definitely keep track on modern versions of C++ because things change. But if we look at this constructor and go over to the right, it says since C++11. So if we actually don't work with a C++11 compiler or a version that supports it, then we don't get this constructor, which is why the demo failed earlier. But when we compiled with the version saying we want C++11 in this, now it works. So this is why documentation is very important and why I should have actually looked this up beforehand. Because if you actually look here, you can see some versions like this constructor right here, there's nothing saying anything about that constructor. So you can use it with any version compiler that you want. Whereas for some other ones, it depends on which version of C++ you're working with. So just be aware of which version you're allowed to use. Try to use the most recent one if you can. But this one, we definitely needed C++11 to actually use it. But thank you for the question, yeah.
So if we wanted to do something like that in an assignment or a lab or something, but you needed to use the C++11 compiler, would we just like send a note also when we turn it in and say that we would like to be compiled that way?
So that question is actually a lot better than you may think. So kudos to you. So for your purposes, if you want to use a different version of C++, I would either email the TA or just put it as a README when you submit your assignment. But in the real world, what would happen is you would create something called a makefile. So when you work with large projects, what would happen is you have a lot of different files, and you want some of them to be compiled a certain way and some others to be compiled a different way, possibly. A makefile says, I'm going to put all of the options for each of the files right in this one file, and then you would just call this makefile with one command, make. And so what would happen is, instead of just saying G++ this file with these options and then G++ this file with these options, it does everything in one swoop. So in the real world, you do something different instead of just compiling each individual file. But for your assignment, what I would do is, because you're only going to have really one thing to compile anyway, so it's not a big deal, I would just send an email to the TA or just send a note when you submit. Okay, enough of that failure. Let's see. Other questions that could make me look more like a failure. Other questions? Okay, so let's look at some of the other stuff for vector. So we kind of saw this already. If we wanted to make a vector larger, we just say pushback on a vector, let's just call it scores, and the value we want to pass in. So if we wanted to increase the size by 1, we would say pushback of 75 or whatever value. If we want to know the number of elements in the vector, we just say dot size. So if scores had 10 elements before, how many does it have after pushback is called right here? 11. Because it pushes it on the back of scores. And so what would how big be after this? What value would it have? 11, yeah, because size would report 11. If we want to make a vector smaller, then the easiest way to do that is to pop off the back. So you may notice pushback and popback. That's actually related to some other data structure we won't be talking about. But if you've ever heard of push and pop data structures, that's where it comes from. What popback does is it takes the last element and removes it from the vector somehow. Yeah, so pops it back. It doesn't return it to you, unfortunately. If you want to actually know what the last element of the vector is, you say dot back instead of pop back. So if we want to do that as an example, so let's make a flat initialization list like this. So like this, and if we wanted to know what is the thing in the last place, and then once we know that element, take it away. So the way that we would do that is say int last element equals array.back. So the way that I figured that out is I went to the documentation and I looked at, instead of just the things in the constructor right here, you look at some of the other functions that you have access to. So the ones that we've been working with are pushback and popback, and placeback does something not completely different. If we want to know what the element actually is, we would say dot back. It will tell you what the element actually is. So what should last element be here in this case? 97 in this case, because it's the last element in the vector. And I'd be very surprised if this didn't work. Yeah, it prints 97. So one demo worked. Good. So if I wanted to know the first thing in the vector, I would say instead of dot back, dot front. And the function for that is here. So it accesses the first element here. So then I should probably change this to first element to make the name make sense. And then if we wanted to see what that is, it'll print 84, and that's the first element, which is good. If we wanted to, okay, that's interesting. So where's push front? So that's in the, isn't that in the slides? So that's actually something that would be really useful, to be able to push on the front of a vector, but it's not in the standard library. So you actually need to do some more manipulation in order to make that work. Let's just go back to looking at the back for a moment, and then let's actually do a pop back here. So what does pop back do? Or removes the last element. So if I do a cout of array.size here, what should it print as the size here? It should print 3, and it does. So yeah, so if you wanted to pop back here, then and then array of size will decrease by 1. And we can actually see that it really did, quote unquote, remove the element by doing a range-based for loop. So another awesome thing about vector is that you can use a range-based for loop in the exact same way as you did before. So I could say for int element in the vector right here, that I can say cout element with a space, for example. And then it prints the 3 elements separated by a space. So it really did, quote unquote, remove the element here. Okay, any questions on that? Yeah.
So you did array pop back, and then you said cout printed out 97?
Yeah, great question. So here, last element is a copy of the element that's in that position. If I did pop back first, then I did array.back, it will give me 92 instead of 97. So, but here it is a copy here. There's a problem if I do a reference here, but we're not there yet as to why that's an issue. But I would just do int or auto, last element equals the vector.back. Other questions?
Is there a pop front?
Unfortunately, no. I wish, but there isn't one. So think about what actually would happen. So if we want to push back, that's pretty simple if there's room. So if there is room, I just put it in that position. I maintain what the last position I've inserted something is, and I insert one position further. So that's no issue. If there's no room, I create the additional contents, and I just copy everything over, put the element in. No issue. What if I wanted to push on the front? So I want the element I'm putting in to be at index 0, the very first position. What would have to happen with the other elements? I have to shift them all. So that's actually a lot harder because we have the representation that we do. So because arrays can't go the other way, you can't have indices less than 0, but you can have them bigger than 0. We have to do this shifting business. If you wanted to have a structure where I don't really care about putting things in the middle of the structure, but I'm going to be inserting things on the end and on the front, then there's something for you, something called a deck. So a DQ in some cases. Yeah, but a deck here is something called a doubly ended queue, which means that if you wanted to do a push or pop front, then a deck is for you because it can maintain going one way and the other way. So if you wanted to add elements on the end, you can do that, or you can add elements on the front. I'm not going to ask you about this, but just know that thinking about what such an operation would entail for one structure, if it takes a long time, there may be a better structure for you. So it depends on how you're trying to access your data.
Couldn't you just use vector insert?
I could do insert, but the thing is that it takes a long time for that to actually occur. You could do that. There's no issue with that. But it's just that it can take a long time. That was a great point. That there is a function for this. Where is it? So there's a general function called insert. So if you wanted to insert at a particular index, then insert is for you. So if you want to insert at index 0 or index 42 or whatever, insert is for you. But the vast majority of the time when you're working with vectors, you deal with one side of it. So you wanted to push or pop on one side of it is what they usually use it for. But you can insert at any place. But you just have to think sometimes about how long certain operations will take. Any other questions? Yeah, so shrinking a vector, call pop back, it'll make the vector one smaller. If you wanted to clear the entire vector, just remove everything, rage quit, you just say .clear on the entire vector, and it just removes everything. If you want to know whether a vector has nothing in it at all, then just call .empty. So .empty will return to you true or false depending on whether it has anything in it. Yeah.
With the clear, does that remove all the points, or does it reinitialize?
Let's actually look, and I'm not going to speculate. Let's actually look. So if we look for clear, so let's look at clear. So it says it erases all elements from the container. After this call, size returns 0. So there are 0 things in the container, in vector in this case. Yeah, so clear really does remove everything. Empty, the function empty just checks if there's anything in it at all, if the size is at least 1. If there is, it returns true, but it doesn't modify anything. Yeah, but clear actually does remove everything. Any questions on vector? Okay, so we do have some time, so I want to start the next section. But nothing after this point will be on the midterm. So we'll only include through vector, nothing on searching and sorting, which is what we're going to talk about next. So here, let's actually solve real world problems. So enough with just like talking about certain structures like arrays and for loops and whatnot. Let's actually solve an actual problem that people really care about. So suppose that I'm supposed to report grades to ASU. So I report grades for each individual one of you. And what ASU is supposed to do is it has all its students maybe in a vector. It has all the students in a vector or array or whatever. And its job is to figure out this 10-digit ASU ID gets a grade of A, for example. This 10-digit ID gets a grade of B. Then what will happen is ASU has to figure out where this 10-digit ID is in its own structure. In the vector of students that it has, where is this 10-digit ID stored? But another example that you may come across, how many of you remember phone books? So how would you find a particular business in a phone book? What would you do? Or a dictionary for that matter. What would you do? Yeah, the pages are alphabetically sorted. So would this idea work? I look at the first page. If the business is listed on there, great, I'm done. If it's not listed, go to the next page. If it's not there, go to the next page. Go to the next page. Go to the next page. If I go through the entire dictionary or phone book or whatever, and it's not there, the thing I'm looking for, is it in that structure? If I looked at every page, no, it can't be there. So would you actually do that with a dictionary or a phone book? No. Why not? It wastes time. What's a better idea?
Use the references. Because you can infer from the name of the business and you can approximate where in the
Ah.
state it will be.
I can infer something from the name of the business. So let's say that it starts with the letter B, for example. But do I know where the B's are necessarily in the dictionary? Could they be like close to the end, potentially? If they're sectioned off, then yeah, obviously I know where the B's are. But suppose it's not sectioned off, it's just a bunch of pages. Where would you look first? Well, assume no index. Because that's actually a better idea. But where would I look?
Probably in the first 10% of the data.
Why 10%? Why not just look in the middle? Because it could be in the middle, it could be near the end, it could be near the beginning. Why the middle?
It's easy to calculate.
It's easy to calculate. So let me try to motivate it a different way. Suppose that I'm thinking of a number between 1 and 10,000. I'm thinking of a number between 1 and 10,000, and your job is to guess that number. So what is a general idea you could try? 1, 2, 3, 4, 5, and then if I ever say yes, you found the number. What's a better way?
Because 5,000.
Why 5,000?
Because short of being lucky, you're going to eliminate the most amount of variables with one question.
So if I tell you that you're too high or too low, then you know if you guess in the middle, you've bisected the list in half. So if I tell you that 5,000 is too low, do you need to search through 1 through 5,000 anymore?
No.
No, because you know the numbers are sorted in this order so that you don't have to search in this part of the list because you guarantee it isn't there. Whereas it could be anywhere in 5,000 to 10,000. So that's the motivation behind this chapter right here. How can you actually search for something in a gigantic a bunch of data. So if you have a large vector of data or array, how can you find something? What can you guarantee if you do something with the structure? Can you do it faster? So we talked about 2 ways of searching. Just search through the entire thing. You don't assume anything about the list. But if we assume what about the list, we can do it much faster. So if we cut the list in half and I don't have to search in the first half, why can I do that? Because it's sorted. So if I know that the list is sorted in advance, I can make the search much faster. So then, because of that, we better know how to sort things. So if we know how to sort things, then we can make the searches much faster. So that's the motivation by why we have searching and sorting together. Because we want to search for stuff, but if we know how to sort, we can make the searches faster. So how do you search for stuff? So a search problem or algorithm is you have a list of data and you have something you want to find, and you want to determine whether it's in the list or not. So if you want to determine whether, what's a business name? Any business. Pizza Hut. Perfect. Taco Bell, yeah. So I want to determine whether Pizza Hut is in the phone book or not. That's a search algorithm or search problem that I want to solve. I want to determine whether it's in the phone book or not. If it is, tell me that it is. If it's not there, tell me it isn't. Pretty simple. So linear search is, I'm just going to search through the entire thing. I'm not going to assume anything about the list. I'm just going to search element by element. If it's equal to the first one, great, it's in the list. If it's not, move on to the next element. If it is equal, great. If it's not, move on to the next element. If we look through every single element in the list and none of them are equal, could it be in the list? No. So therefore, we can do linear search pretty easily. And binary search is the one I talked about before, cutting it in half, but we'll get to that later. So look at this list right here. So there are 7 elements in here. And let's say we're looking for 11. So first off, is 11 in this list?
Yeah.
Great. So because we can look at it. But a computer can't just look at this because our computer's smart or dumb?
No.
They're dumb. So it says, okay, is 11 equal to the first element in this list? No, because 17 is not equal to 11. So we move on to the next element. Is 23 equal to 11?
No.
No. 5 equal to 11?
No.
11 equal to 11? Yes. So by that reasoning, is 11 in the list? Is 8 in the list? No, because what will happen is you look at each one of these 7 elements, and none of them are equal to 8, and so it's not in the list. Pretty simple. So the benefits for this are it's super easy to implement because we can just use a range-based for loop for it. So, or a normal loop, but we can use a range-based too. We can just say for int element in the array, in the vector or whatever, if the element we're looking at in the vector is equal to the one we're searching for, then it's in the list. If we go through all of the elements in the vector, which means exit the for loop without having found it, and we find, oh, you never equaled anything in the list, it can't be in the list. And the great thing is that no matter what the element order is in the list, it just doesn't matter. It will always work. So it doesn't matter if it's sorted or not. Sequential or linear search will always work. The disadvantage is that it's really, really, really slow. So I've actually noticed this sometimes when I was doing a linear search through a list, and then what I noticed is that it was really slow, so that then I sorted it first, and then did the binary search, which we'll talk about later. And then I saw a speed improvement of over 100 times. So because there's so few searches compared to linear search. Linear search is way slower. But actually, that's not true either. And we'll actually hopefully see that next time. So I'll see you on Monday.